All right, so again, this is an extremely important tool, especially the Cepheid variables that Henrietta Leavitt first discovered. And anyhow, it's a tool for allowing us to measure distances to even further than we could with spectroscopic parallax. Okay. Oh, and you look at this. I should have known this was coming. Okay, so within the solar system, very we can measure things using radar, so you can actually send electromagnetic signal. For example, one of the big ones that we use is bouncing radar off of the moon, bouncing radar off of the planet Venus. It doesn't work with the sun because the sun would have just absorbed that radiation. But anyhow, things within the solar system, a comet, an asteroid, something like that. We can use radar. We can also, within the solar system now, of course, in modern times, we've sent spacecraft, and we can make more accurate measurements to distances within the solar system using radar and the technology of spacecraft as well. So if you go out, beyond the solar system, so this is would be more than a lot more than 1 astronomical unit. So you're talking about more than, like, let's say 1,000 astronomical units, or even more than that, obviously. Then you use what's called stellar parallax, right? We discussed this in great detail. So we use the orbit of the Earth itself as the baseline, and then we look at a star and we look at the slight shift, the slight angle that we see, the difference that we see with as far as where the star is, 6 months apart, and so it shifts with respect to background stars much further away, and so we measure that shift. We know what the baseline is, and so we can measure that. That's a direct way of measuring what's called stellar parallax. Remember that only works out to about 200 or so, 250 maybe parsecs, 200 about 200 parsecs with any decent accuracy. Now we can go further than that, by the way, now, and we can actually go almost to with the Hipparchus spacecraft, which was, I think, in the early 90s, maybe it was in the early 2000s. It might have been in the early 2000s. And now, more recently, the European Space Agency sent up a spacecraft called Gaia, and that has extended the baseline, basically. So the baseline is much greater, and so we can measure stellar parallax using the Hipparchus and Gaia data. Now, of course, Gaia hasn't been up in space for a great deal of years, so we only have limited data. It's got to have time to photograph as many stars as it can. Take photographs of as many stars as it can, and then we go and we can measure these things. But anyhow, we think that it's going to extend our range almost to 10 kiloparsecs, 10,000 parsecs, which is the original distance that the spectroscopic parallax got us. So the nice thing about that is using Gaia data, we can check ourselves against spectroscopic parallax. All right, so let me remind you what spectroscopic parallax is. So you find the color index. Remember, the color index is what temperature. Remember, these are temperatures. This is O stars are the hottest, M stars are the coolest. And so what the temperature is will give you on as long as it's on the star is on the main sequence, it'll give you what the luminosity is in solar units. So if you can figure out what the exact, or as exact as you can, the color index, or in other words the type of star that it is, you will know what luminosity you're looking at on an absolute scale. And so then you use the inverse square law, right? Where, remember, the flux is equal to whatever the luminosity is divided by 4 pi 4 pi times r squared, where r is the distance from the Earth to that particular star. So that works. Out to about 10,000 parsecs. Remember, the further out you get, the less certainty you have. But like I said, now with Gaia data and even Hipparchus data, which is older, we can actually use stellar parallax to check these numbers. All right, so. And then, of course, this is the next level. So the thing that's important about variable stars, or really the periodic variable stars, that not just any variable. Some stars vary, but we're talking about like the RR Lyra, the Cepheid variables, or even Myra variables, which is another class of variables. That'll extend us out from 10,000 parsecs out to 25 million parsecs. So now you're talking about galactic distances. We're looking further and further out into the universe. So this is well past where like the Andromeda galaxy is. So you're picking up a whole bunch of galaxies by looking and seeing Cepheid variables. We can measure distances to these galaxies, and of course there's other ways that we're going to talk about. But see, this is what we talked about, the cosmic ladder to figure out further and further distances. And again, it's very important to be able to check, like this part with variable stars will bleed a little bit into the next part. Which I think, what's the next part? I think we're going to use what's called the Tully-Fisher method. I think that's the next step. Anyhow, it has to do with galaxies themselves. All right, so let's continue. All right, so let's see. So as it says, so this is now how do we figure out the shape of the Milky Way? So it actually goes to this one guy, well, not just one guy, but this guy named Harlow Shapley, who was an American astronomer in the early part of the 20th century. So he was actually alive when Henrietta Leavitt had made the discovery that you could use Cepheid variables as distance indicators. So what he did is he took some of the RR Lyra variables found in these globular clusters. So let's talk about what a globular cluster is, even though we've discussed this before. These are spheres of very just a great number of, it's basically a cluster of anywhere from hundreds of thousands, so some of these clusters have hundreds of thousands of stars, to all the way up to maybe 1 or 2 million stars. All right, so these are clusters of stars, but they exist outside the plane of the galaxy. They actually exist in a halo around our galaxy. Now what I'm about to what we're talking about is how Harlow Shapley actually discovered that, and indeed discovered our place in the galaxy. that we're nowhere near the center of the galaxy. Okay, so what he did is using these RR Lyras. Remember, these things, a lot of them you can see outside the plane of the galaxy, right? So you can look in directions not along where the disk of the galaxy is, and you can see these globular clusters. And so some of them, of course, are, there's some RR Lyra variables, and he used the fact that their absolute luminosity is roughly 100, and then he measured the apparent magnitude, and then determined that these things were a long ways away, like really far compared to some of these stars. I mean, they are thousands of parsecs away. All right, so here, let's see. So let's see. That's actually talking about. Well, here, look. Let me look at the next slide. Let's see. So they're going to talk about the like Henrietta Leavitt and Annie Jump Cannon and so forth. The people who were called computers by Harvard. These ladies that were hired as computers. Anyhow, let me go back to the globular clusters and the story of Harlow Shapley. So what he did is he said, okay, I can figure out the distances to these different objects, and he basically made a map of the globular clusters, and he said, well, it seems to be reasonable that they would be clustered around the center of the galaxy, which he, like everybody else at the time, thought was the sun. They thought that the sun was the center of the galaxy. And in fact, during his time, they didn't even know that other galaxies existed. That comes a little bit later, as you're going to find out with Cepheid variables. So when he did this, he realized that the sun was about 2/3 away from the center. He came up with that 2/3 number, but by looking at this at the globular clusters and realizing that was basically they surrounded the galaxy, and so we were about 2/3 of the way out. And the number he got, though, was not accurate, because at the time, so remember, this is over 100 years ago, astronomers didn't take into the account, gas and dust, what we called reddening due to gas and dust, which was, I think, in chapter, was it 18? Chapter 17 or chapter 18, I think. Maybe it was chapter 18 or 7. I don't remember. Anyhow, when we first started talking about gas, the reddening due to gas and dust, he didn't take that into account, and because of that, he didn't get a correct number for the distance between the center of our galaxy and our sun. Now, in modern times, it's about 8.5 kiloparsecs. So this is an approximate value, 8 kiloparsecs. So 8,500 parsecs is roughly the accepted distance between our sun and the center of the galaxy. All right. And by the way, the center of the galaxy is, when you look at the Milky Way, it is thickest, the most concentrated in the direction of Sagittarius. And guess what? This is the direction of, when you look out into the night sky, the direction of Sagittarius is the direction of towards the center of the Milky Way galaxy. Now, we can't see in the visible part of the spectrum the center of the galaxy, but that's a different story. We're getting to that. We use, of course, radio waves and infrared waves that certainly were not available to people like Harlow Shapley. All right. So I mean, this was actually, just kind of think about this for just a moment. This was a big step, almost the way Copernicus took remember, the Earth was considered the center of the universe, And then Copernicus said, no, the sun was the center and the Earth just goes around it. Now the sun isn't even the center of